We already heard this morning a bit about quantum networks. This is one of the big ambitious goals of quantum technologies, to build a large-scale network of processor and quantum nodes that can kind of share and process quantum information and realize a lot of very cool applications. And how we envision this network to be is with photonic interfaces for the nodes, such that we can use photons to get the quantum information around in the network, and use these photonic links to generate entanglement between remote nodes. And this is kind of crucial because the entanglement is the main resource that we use for most of these nice advanced quantum network applications. Now, in practice, there's many different hardware systems that are being investigated or proposed for realize such quantum nodes, which to me makes a lot of sense because each one of these has different properties or features that are maybe optimal for some specific tasks of the network, like processing, routers, memories, and so on. So it's, for me, but not only for me, it's a bit hard to imagine that we're going to have this complex and functional network only using one system. So we need to kind of build this network with a hybrid architecture, by which I mean an architecture that allow us to host different type of hardware in the network and also connect them together. So along these lines, today I want to introduce, first, I want to talk about entanglement protocol, so protocol for generating remote entanglement, and in particular, a framework that you can see these protocols in a general way that's a bit independent of the actual hardware. And then I'm going to take some of these concepts and show an idea for connecting two important parts of the node, which is a quantum node and a quantum memory, and talk a bit about how we want to implement it in the lab. So, as I said, there's many different platforms ranging from trapped ions to neutral atoms to various defects in solid state systems. And for most of these platforms in the last couple of decades, there's been an experimental demonstration of entanglement. And if you look at all these papers and all these demonstrations, there is kind of like always feels like the protocols that are used are very tailored and specific for each properties and for each platform. Which sometimes kind of gives rise to a bit of zoo of protocols and can be a bit overwhelming. Well, actually, they have a lot in common, a lot more in common. And with this spirit, a couple of years ago, with some collaborators in my previous research groups and in MIT, we decided to put some order and build up a framework, theoretical framework, for categorizing this protocol, breaking them down into building blocks that have not necessarily anything to do with the hardware, and that allow you to kind of connect them together, sort of like Lego bricks, to think and design new entanglement protocols for different hardware systems. So the way this framework works is by taking a protocol and dividing into layers of abstraction, starting from very, very general concepts and building blocks that we call logical building blocks or functional building blocks that really just realize a function in the entanglement protocol, like a measurement or a photon source or a spin photon interface, which, as you can imagine, is the most important one, and really have nothing to do with the hardware that they are implemented with. And then you can kind of break these building blocks down into more details of the implementation and put more details of your hardware down to the point where you can really kind of have a full quantum optical description of your system and use it, for example, for simulations. Now, if I had more time, I would go through and explain you how this framework works in details, but I don't, so I will just give you two examples of how you can use this framework, because maybe you realize that it's useful for your case, and maybe you read the paper, which is a bit long, but definitely worth giving it a shot. So first, let's say that you are interested in realizing an entanglement protocol, but you don't really necessarily need to know anything about the implementation. Maybe because you're interested more in the architecture of the network, right? So you can take these building blocks and put them together to form entanglement protocols. And actually, all of the protocols that we found in the literature and what that we could think of, they can kind of be categorized in three different topologies that you can think of, kind of the direction of flow of the quantum information in the protocol. And then you have, for example, you can take your spin photon interfaces, which is your two nodes that you want to connect, that are going to be entangled with photons, and send the photons to a midpoint source where you do some detection or Bell state measurement that you use for entanglement swapping. Many of you might recognize this. This is one of the absolute most used entanglement protocols in most platforms. But you could, for example, also say, okay, I have one node and I kind of entangle it with a photon, and then I send it all the way to the second node, and then I kind of herald the interaction and measure it, and this also kind of realize entanglement between the two nodes, and this is also kind of used in many cases. Or you could generate the entanglement in the center and then send it outwards to the nodes. And then this is a bit less used, for example, in single emitters, which is kind of the focus of what this framework was at the time. But it's also kind of can be used, and it's, for example, useful in case you want to do satellite. Want to use satellite for realizing the entanglement. And these kind of ideas already give you a lot of information on how your entanglement protocol works, but have nothing to do with the hardware so much that you can actually write all of these kind of architectures simply into circuit diagram operations. And then, if I would ask you, what do color centers in the diamond have in common with neutral atoms? Is that, for example, you can realize entanglement with both systems using the same architecture. This is two works: one with silicon vacancy centers, one with rubidium atoms in fiber cavities. That, of course, the implementation and the actual how the spin photon operation is realized is different. The encoding is different, but the architecture at a high level is the same. Then, of course, you can go deeper and figure out how the details of the thing of these protocols are. This is what we've done in the paper. So if you're interested, you can look it up. But you can also look at it from the other way around. Say that you're an experimentalist. You already have your own favorite platform. In our case, back then, it was the Silicon Vacancy Center, for which we could get a very good quantum optical modeling with some parameters, some experimental parameters. And what you can do is combine these building blocks into different protocols and compare them. This is also a study that we've done, theoretical studies and simulations that we have done in our work. And we actually, with the paper, we also published open source repository for realizing such simulations. And I mean, in our case, it was a pretty kind of like simplified system, and we compare different type of protocols with different topologies and different realizations of the spin photon gates. And this already kind of can give you some information on the performance of one protocol over the other. For example, we figured out that using single photons is much better than weak coherent state, although we kind of already expected it. But also that, for example, in this system, using spontaneous emission is actually more efficient than using this kind of single photon or scattering over a cavity, and so on. If you have a more detailed model, you can also, for example, try changing and sweeping the parameters of your system and seeing how these protocols perform in different parameter regimes, which could actually be very useful. In our case, we tried, for example, changing the cooperativity of the cavity emitter system and saw how one of the protocol was performing, and kind of this can give you an indication, for example, where to improve your system, where it's actually not useful to improve it. For example, we have noticed that doesn't make a lot of sense to boost the cavity cooperativity too much because at some point it saturates, and so on. This is kind of to show you how this protocol can be used if you have a system and you want to kind of explore different applications. Now, we have done it with one specific case, but in principle, all of this framework is independent of the hardware, and you could apply it for whatever you want. Now, this protocol, this framework is for direct photon transmission, which is fine if you want to do entanglement at a very short distance. But if you want to go to a very long distance, like hundreds of kilometers, this doesn't work. We already heard about it this morning. You have photon loss in the communication channel, which prevents you from doing that. So the solution is using quantum repeater schemes, where you basically need, you want to break down the distance in smaller segments, and you want to use memories, quantum memories, to kind of then take these entangled smaller segments and kind of fuse them together with Bell state measurement and kind of expand the entanglement between the two faraway nodes. Now, in our group in ICFO, we are working on these platforms, like these memory platforms, and we kind of mastered in the years how these kind of like in between segments of the repeater scheme using rare earth ion crystals, quantum memories. And maybe yesterday, if you were paying attention, maybe you saw the talk from Anta, who explained how these memories that we use in the lab are. What we want to do now, and what we're kind of like starting to look into, is actually the end of this chain, where you want to connect your quantum node to your quantum memory, which is kind of very important, because then you kind of, it's a fundamental element if you want to realize this whole chain. So you can look a little bit how our memory system works with the same kind of building block idea that I showed you before. We have a photon pair source, which sends one photon compatible to the quantum memory, and another one in the telecom range that goes to a Bell state measurement station, which is what we usually use to kind of connect all of these links. Well, what we need to do in order to do what we want to do is just take a spin photon interface, like a node with a spin photon interface that's compatible with the memory, and we can then just realize the bell state measurement between the spin photon interface in the node and the photon pair source that connects to the memory. So actually in the lab, we started working on this, and in order to do this, you need a quantum processor which has an efficient light matter interface. And of course, you need it to be compatible with the SPDC source, because by what I mean by compatible, you want to be able to realize the bell state measurement, so you need your photons to be compatible for kind of a two-photon interference. So how we are trying to do this in the lab, very briefly, we have such a system that we can use as a quantum network node. And it is a Rydberg Suter-Atom setup that we have used, that was used in previous experiments. It is a very cool system because it basically combines elements of of Rydberg atoms, in the sense that you can only have one excitation. So basically, you can, if you have a cloud, but it's smaller than the actually blockade radius of the Rydberg interaction. So if you excite, you're only going to have one excitation, which gives you single photon generation capabilities, and you can encode a qubit in it. But you still have the ensemble effect, so you can get efficient light matter interaction, which scales with the number of atoms. And we have this setup, and we are kind of vamping it up, adding an external cavity to make this interaction even more efficient. And we have designed a pretty high finesse cavity for this type of systems, which would allow us to work at very low optical density of the cloud, so only a few hundred of atoms. So that, and in this kind of like low density, we can already saturate the retrieval efficiency, so basically the emission of photons in the mode compared to the emission in free space. And this allows us to kind of also have a slightly better system and a slightly more efficient system. And very briefly, we're also at the same time trying to work on how to get the compatibility of the photons emitted by this rubidium superatom by using a much simpler setup with just a mod, to kind of testing how the qubit encoding, which we plan to do with time-being qubits, which is compatible with our memory, and the photon shaping, and especially doing the quantum frequency conversion, because of course then you want to bridge the wavelength difference between the rubidium atom and the infrared, the telecom photon that's coming from the memory. So this is kind of something that we're working on right now. So I talked to you about entanglement protocols and a way to design them and kind of understand them in a way that's a bit independent of the hardware platform. And I also showed you a bit how you can have this for connecting a link, not a link, that's a typo. You can use this to create a link between a quantum node and a quantum memory, and how we're trying to implement it in the lab. I will briefly want to thank the QPSA group in ICFO, especially the people working in the cold atom teams, and all the people in the previous group and from MIT, with which we developed this nice framework for entanglement protocols. And with this, I am done. Thanks.
We have time for a short question. If not, there is time for a curiosity of mine, not exactly related to your talk, but you mentioned long-distance entanglement. And which is the target of your network in kilometers?
This is something that's a bit more related to the other project of the lab, which is on the quantum memories. So I'm not the right person to reply to this, but we can chat maybe later with some other colleagues, and I can give an answer to this.
So let's thank the speaker again.